All right, let's talk. We've all been there. The app is slow, and the first thing everyone says is, just add a cache, right? It's become this default knee-jerk reaction for any performance issue. But what if I told you that that silver bullet we all reach for is actually a landmine? Today, we're going to bust that myth wide open and really dig into why your Redis strategy might be setting you up for a total catastrophic failure.
And that really gets to the heart of it, doesn't it? This quote from Nelson Elhaj at Anthropic just nails it. Performance isn't some extra thing you bolt on at the end. It's a core feature. Think about it. A fast tool feels powerful, you trust it. A slow one, you just stop using it. And caching is supposed to be our #1 weapon in this fight for speed, promising to serve up data from memory like 10 to 100 times faster than hitting a database.
So you do it. You spin up Redis, you point your application at it, and boom, the latency numbers plummet. You look like a hero, right? Problem solved. Well, not so fast. This is that exact moment where a lot of well-meaning performance fixes start their slow, quiet journey toward becoming the next big production outage.
And here's why the stakes are so incredibly high. Just look at the complexity of the systems we build today. In an architecture like Uber's, a single tap on your phone can fire off requests across 500 different microservices. In that massive web of dependencies, a cache that's acting up doesn't just slow one thing down. It can trigger a chain reaction, a cascading failure that brings the entire system to its knees.
So, to figure out where things go wrong, we've got to go back to the fundamentals. To avoid these traps, you need to know the plays. Let's break down the 3 core caching patterns that, honestly, every single engineer should have in their back pocket.
First up, we've got cache aside, or what a lot of people call lazy loading. This is the absolute workhorse. It's the most common pattern you're going to see out there. The logic is super simple. Your application code is the boss. It asks the cache, hey, you got this for me? If the cache says nope, the application basically says, okay, cool, I'll go get it from the database myself, and I'll stick it in the cache on my way out for next time.
And this is what that flow actually looks like. The app asks the cache, whoops, it's a cache miss. The data's not there. So the app has to do the slow, heavy lifting, go all the way to the database, pull the data, write it into the cache, and then finally send it back to the client. The key takeaway here is pretty simple. With cache aside, the very first request for any piece of data is absolutely guaranteed to be slow.
Okay, next pattern, write through. This one takes a totally different approach. Instead of being lazy, it's super proactive. Whenever your app needs to write or update some data, it writes it to 2 places at the exact same time, the cache and the database. The whole point here is to achieve strong consistency. The idea is that the cache should never have stale, outdated data.
So the write operation itself isn't actually considered done until both the cache and the database say, yep, got it. So what's the catch? It's latency. Write latency, to be specific. You've just chained the performance of your user's request to 2 different systems. If your database is having a slow moment, your cache write is slow, and your user is just waiting. And now for the real high-risk, high-reward pattern, right behind. This one is all about pure, unadulterated speed. The application just yeets the data at the cache and moves on with its life. The cache says thanks almost instantly, and then, sometime later in the background, it gets around to writing that data back to the permanent database. It's amazing for write-heavy stuff like analytics or logging.
So how in the world do you choose? Well, this table really lays out all the trade-offs. Cache aside is simple, it's pretty safe, but you're going to pay a price on every cache miss. Write through gives you that rock-solid data consistency, but you're paying for it with slower writes. And right behind gives you ridiculously fast writes, but you have to accept eventual consistency, and this is the big one, you risk losing data if your cache crashes before it gets a chance to save it. There's no best pattern here. It's all about what you care about most: speed, data safety, or simplicity.
All right, so you've picked your pattern, you're feeling good, you're safe now, right? Ha, nope. This is where we get into the really nasty stuff, the hidden failure modes that can turn your beautiful cache into a ticking time bomb in production.
In this quote, this gets to the absolute core of the problem. The issues we're about to talk about aren't things you can fix by tweaking some config file. They are fundamental, architectural challenges. You have to start thinking of your cache as a core part of your system's design, not just some add-on. So, welcome to what is famously one of the 2 hardest problems in all of computer science: cache invalidation. It sounds like such a simple question, but the answer is brutally complex. When data changes in your main database, how do you tell your cache about it? How do you make absolutely sure you are not serving old, incorrect, totally stale data to your users?
And here is the real-world cost. Imagine your marketing team just launched a massive sale. The price of a hot product just dropped. But your cache, it's still stuck serving the old, higher price. Now you're not just creating a confusing user experience, you are literally losing sales and destroying the trust your users have in you. That's the business impact of getting invalidation wrong.
And then you've got this nightmare scenario, the cache stampede, also known as the thundering herd. Picture this, a super popular piece of data, maybe the homepage for a news site, is about to expire from the cache. The very nanosecond it expires, hundreds, maybe thousands of user requests all miss the cache at the exact same time. They all stampede directly to your database, which was never, ever designed to handle that kind of load. And just like that, it's down.
But the complexity doesn't stop there. See, caching isn't just this one little box that lives next to your database. It's a systemic property. It's a strategy you have to think about at every single layer of your stack.
I mean, we see it everywhere. At the application level, we're caching user sessions and configs. Down at the database level, we're caching query results. Out at the very edge, you've got CDNs, content delivery networks, caching files and API responses in locations physically closer to your users. And in the new world of AI, it's getting even wilder. We're now using things like semantic caches to store the meaning of an expensive query to a large language model so we don't have to recompute the answer every single time someone asks, how do I change my password in a slightly different way?
Okay, we've seen the patterns, we've seen the terrifying ways they can explode, so how do we actually build a caching strategy that's a real performance multiplier and not just the cause of your next all-hands-on-deck production fire? Let's get into the practical, actionable stuff.
First things first, you can't fix what you can't measure. You have to start by watching these 4 golden signals. Your hit rate, that tells you how effective your cache actually is. Memory usage is your early warning system before you just run out. A high eviction count is a giant red flag that your cache is probably too small for your workload. And keeping an eye on connected clients can help you spot nasty things like connection leaks before they crash your whole server. And here it is, a concrete, 5-step plan you can take back to your team. First, measure everything end-to-end and set a budget, especially for your P99 latency. That's the experience of your unluckiest 1% of users, and it's where the real problems hide. Second, use tracing to find your actual bottlenecks. Third, simplify your architecture. Get rid of unnecessary network ops. Fourth, add smart controls like deadlines to cut off those super slow requests. And finally, number 5, design your system to fail gracefully. Assume things will break and plan for it. And this quote just brings it all home. A cache reduces work most of the time. A truly resilient strategy isn't about chasing a 100% hit rate, because that's impossible. It's about accepting that cache misses will happen, and sometimes they'll happen all at once in a big storm. You have to design a miss path that is fast, efficient, and won't obliterate your other systems when it's under pressure. So I'm going to leave you with this one question to take back to your own team, to your own systems. Take a hard look at your architecture, your monitoring, and how you handle failure. Is your cache really a performance multiplier, something you've thoughtfully designed to be resilient? Or is it a poorly understood black box, just sitting there, waiting for the right set of circumstances to become your next major production incident? The choice really is yours.